Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL course on building energy systems and auditing. We are in the module number 5, energy conservation and thermal comfort we are discussing, and in the last lecture of the module number 5, lecture number 25, we will discuss about the thermal comfort indices. In the last lecture, we have discussed about the various components of the thermal comfort, and in this particular lecture we will going to have the discussion on effective temperature, operative temperature, the predicted mean vote and predicted percentage dissatisfaction, and tropical summer index. As we understand from the last lecture that these 6 parameters are very much responsible, or parametrically it is responsible for human thermal comfort. There are parameters like air temperature, mean radiant temperature. We have discussed mean radiant temperature thoroughly in the last lecture. The air speed, the velocity or the speed of the air, the humidity, that is the relative humidity of particular in a closed condition. These 4 are the thermal parameter, or you can say it is the environmental parameter. The 5th and 6th activity, which is the metabolic rate, and the clothing or the personal human parameter. So, these 6 parameters can be classified or can be treated as a parametric variation by virtue of some numbers, and based on that a composite score or index can be generated, and we will discuss today that how that kind of index can be generated, and that can be give us a kind of indication that which is going to be which combination is going to be comfortable or not. So, it is this old one that we have discussed in the very second or third lecture probably, the psychometric chart. In the psychometric chart, as you know, that is in the x axis it is the dry bulb temperature, y axis is the humidity ratio, those curved lines are the relative humidity curves. So, based on this particular the psychometric chart, let us assume a boundary. Let us assume a boundary. That boundary will be defined with the typical 2 dry bulb temperature and also 2 curved lines of the relative humidity. So, I am assuming, this is my assumption, let us assume that the 20 degree centigrade to 30 degree centigrade, these 2 lines are coming under the within that temperature or in the comfort temperature or so, whereas the 40% relative humidity, which is the lower curved line, and the 60% of the relative humidity, which is the upper curved line, are come under the in between this 40 to 60% of relative humidity will be considered to be the comfort zone. So, within this particular the bounded area, any combination of the dry bulb temperature and the relative humidity will satisfy the thermal comfort condition. Let us assume that, and anything outside this particular point will not going to be that, or maybe if it is lower temperature, less than 20 degree temperature or whatever. So, those points are not going to be considered as a thermal comfort conditions or so. Let us assume that. In this respect, what we can do, we can go to the psychometric chart, and let us suppose this is that particular boundary 60% RH to 40% RH, 20 degree centigrade dry bulb temperature to 30 degree. Now, there may be several situations inside a closed environment because of a lot of heat production or maybe lot of loss of heat, there may be several conditions, or maybe there is a there is maybe some kind of the natural ventilations which is moist air, or maybe there is a heavy amount of latent heat generation inside a closed air conditions or so. There can be n number of situations or causes may be there which may create some kind of discomfort. So, suppose let us take the first point like this, if it is a hot and dry, the hot and dry means the temperature are more than 20 or maybe more than 30 or something like that, and also it will be having very less amount of the humidity. So, that it will be lower than the 40° RH line. So, I have considered two such points. So, one point just below that particular the area. So, I have to put it up, I mean what I have to do, I have to somehow have to do some physical change or maybe some changes in the inside the room, maybe some mechanical ventilation or anything that will going to push this particular black point to inside here. Then I will have that kind of a comfort, because the condition which not at all suitable, it is very dry and temperature wise it is maybe fine, but it is dry. So, I have to be little bit increase the moisture content in it. So, I have to be thinking of the or the humidification, not dehumidification, humidification of the particular case. The second case, you see that the right hand side the dot, which is a dot or the state of temperature and the relative humidity, which is maybe less than 40% humidity, but the temperature is very high, it may be more than 30° or maybe 40° or so. So, that is also not going to be suitable for the thermal comfort. So, again that has to be pushed up and place it to this particular point, that within that particular red the boundary zone, and that will be push in the way, it is not going to be the vertical push, it will be a slanting push towards up. So, that means you require some kind of a cooling, and also it requires some kind of a the evaporative cooling, because it is going towards the same WBT line or parallel to the WBT line or so. The first one is the upward push, that means there is a no change of dBT. So, it is a kind of a humidification, no cooling or no heating, sensible loss will not be there or sensible gain will not be there. But in the second case, it is a slanting push. So, it will have both, it will have a one component of the cooling component, sensible cooling component, and another component of the humidification component. Let us see another 2 points which are in the warm and humid zone, because why it is warm and humid? Because warm, because it is the temperature is higher side, and humid because the RH is also going to is a higher side. So, take the first top point, central one, you have to push it down if you want to manage it, or if you have to provide some kind of a thermal comfort. So, to push it down, you have to cross the line of 60° humidity. So, you have to reduce the humidity, you require dehumidification, but no sensible heating or cooling is required over here. Whereas, if you go to the other point, which is your sensible cooling and the dehumidification point, I mean that will be the action. So, you have to push it inclined towards down, and it required both the component, that is the cooling also, and it is also required some kind of the dehumidification. So, and finally, maybe you have a very cold atmosphere or maybe cold interior, and you require some kind of a sensible heating just to push that particular black line, the leftmost black point, put it inside that particular red boundary zone or so. So, we understand this, these two are the prime factor maybe that we can think of, that the relative humidity and the dBT is going to have a primary role. So, we can go little back, and then we can say that these two are maybe we understand this combination of this air temperature and the humidity will going to plays a role. But we will see that how this air speed will be now going to take, and Mean radiant temperature we discussed earlier. So, it has a combination of the air temperature and the air speed also with some kind of radiant heat. So, this is also going to be taken into account in further discussion. So, the first discussion we have taken into account the relative humidity and the DBT. Then we can discuss the third one. So, the first addition is the air velocity. So, and this particular, if I take air velocity also into account, with that is called the effective temperature. So, what is effective temperature? It is again a combined factor of these three, the dry bulb temperature, the relative humidity and the air velocity, such a way that it can now participate in a way, it can give a kind of a situation under these three combinations, something is higher, something is lower. So, in that particular situation, how a human body or react to the thermal comfort scenarios or so. So, in this particular monogram, we can see this particular monogram, if you see, it has two axes or two side axes, we may say. The left side is the DBT, or you can actually take GT. So, GT is your globe temperature, which mostly tend to indicate the mean radiant temperature. This GT, we are assuming here that the DBT and the globe temperature is more or less same kind of a scenario. The right hand side scale is the WBT. So, it is your wet bulb temperature. So, even if you take this DBT, if you take the DBT plus this WBT combination, in fact, that is going to lead to the DBT and RH combination. These two are already taken care of. Here what is happening, if you, this is R, if we are taking the GT, the globe temperature. So, that means we can say this is R, the mean radiant temperature we are taking for this particular the combinations. And other axis, there is third axis also, or the third parameter also, which is the air velocity in meter per second, which starts from 0 or something like that, and 0.1 maybe, and 0.5, 1, 1.5 to 7, and it is from 1.5 onwards is very high velocity. So, sometimes I may start the ceiling fan, or maybe some kind of a stand fan, or maybe there are really ample amount of natural ventilation coming in through the windows or so. Based on these three combinations, we can see that where is the comfort. The comfort is given as this shaded this line. This is ET. ET is the effective temperature. It is the effective temperature or comfort effective temperature. Now, how I will going to decide about, suppose my DBT or MRT or the globe temperature is 40 degree. In that time the WBT is about suppose 20 degree or so, this is the 20 degree. So, I will draw connect these two line. So, if I draw this connect these two line, so it goes like this. So, any combination of the air speed will not give me any kind of the comfort, or the effective temperature is not come under the comfort scale also. The effective temperature lie between almost like the 25 degree to 30, not 30, 20, 26, 27, 28, this is 28 degree or so, 26, 8 degree, this line is the 28 degree line or so. So, it is not coming comfort. Suppose the maybe I let us say that this is maybe 12 degree or so, 13 or 13 degree, this is 13 degree DBT. Then probably with the same combination I am passing through this particular dark color zone, which is a comfort zone, but this comfort zone will not be suitable for all the combination of the wind velocity or the air velocity. Its comfort with these two combinations of WBT and the wet bulb temperature, the comfort comes on 0.1 to 0.2. So, this is the all these 4 lines, these 4 lines are 0.1 to 2.0 meter per second the wind velocities are. So, on in between that there can be a comfort, but it is relatively look like it is the temperature which is about 22 degree to 26 degrees or so, 22 degree to 26 degrees or so, that kind of temperature can be maintained. But this passing through lines is passes through almost about 20 to 21 degree, something like that, which will going to be look like it is not 20, sorry, it will be around 25 degree, around 25 degree temperature to be, even if it is the dry bulb temperature and the is much higher 40 degree, but because of the air velocity and because of the humidity present in that particular air, it will effective temperature will be around 25 degree. So, this is these two are now combined with the air velocity and that lead to the effective temperature. So, this is one of the criteria, and we can go to the operative temperature next. The operative temperature are another way to look into the S-ray and other type of the indexes as actually taken into the operative temperature in nature. This is also you see it is the MRT, DBT and your velocity, that V stands for the air velocity. These 3 things is now here taken care of. So, here it is the 3 things MRT, DBT and the air velocity is taken into account, and this is the typical formula for that, and where the air speed is very low, mostly it is stagnant kind of a scenario, 0.1 meter per second or something like that or below that, then this bracketed terms will be or the under root terms will be going to be 0 or very small, and then it can be redefined. It cannot come from the directly from this particular equation, but it is redefined as the operative temperature is MRT plus DBT. This is not BDT, sorry, this is a mistake, this is DBT by 2, and this MRT plus DBT by 2 is almost most of the time we have taken this as the operative temperature. So, what is operative temperature? It is a simple a kind of a composite index of the temperature, which like effective temperature, where the MRT and DBT and the velocity of the air is taken into account, then the combination of these 3 can give a certain temperature which is not equal to MRT, which is not equal to DBT, which is not equal to WBT, which is new combinations as operative temperature, which you may say that which human may feel as our brain may map that kind of temperature as a operative one. So, this is the thermal comfort scaling which is superimposed in psychometric chart given by the ASHRAE 55 2013. So, this is a very interesting kind of a curve, because it superimpose the zones of the thermal comfort, number 1, and number 2, it superimposed various zones of thermal comfort based on the flow values. So, it has actually the 0.1 flow zone. See, this is the first boundary, the not 0.1, 1.0 flow zone. So, it's normal kind of the clothes, and there is little less 0.5 flow zone, and these two are the basically 2 flow zones. So, if you are have little bit of heavy garment or so, then the first shaded area will be the comfort zone, which is operated maybe from 22 degree to 26 degrees or so in the DBT, sorry not DBT, operative temperature See, there is another change. In the x axis it is not the dBT, it is the operative temperature mentioned in degree centigrade, half of the dry bulb plus half of the MRT for steel air, yes, in case of the steel air. Now, if this is 0.5, little bit of more temperature, 25 degree to almost 27 degree or something like that, it is 0.5 flow, it is a kind of a comfort, but you see there is a, in that particular little darker zone, it is written 0.1 meter per second airspeed is required to maintain that particular comfort. The first one you do not record any kind of the air velocity, maybe you do not need any kind of natural ventilation, you may not need any kind of the ceiling fan or any kind of a fan, it is normal. The third zone determines the very lower amount of clothing with a very low metabolic rate and very low kind of mean temperature, but you need more the higher amount of the speed 1.2 meter per second. So, as and when you go sliding towards the left to right, you require more amount of the air speed and you require less amount of clothing values also. So, there are 2 main and 1 sub zones. So, 3 zones maybe you can say, and then this has been devised as the one of the basic fundamental requirement of the thermal comfort from the ASHRAE 55. This is another one, operative temperature of ASHRAE, they have also given like that. The mean monthly outdoor temperature is in there. This is also very important and very crucial. The composite index you may actually think for if you go for any kind of audit. We will discuss in the next class, next chapter, or maybe the next to next one. So, in case of the energy audit or so, somebody is asking for little bit of comfort, you can actually see that whether the comfort is required or not based on this particular chart or based on the earlier one. So, monthly mean outdoor temperature in the y x axis, of course, x axis and the y the upper axis are same, which is only the degree C and the degree Fahrenheit, and the indoor operative temperature is in the y axis. So, operative temperature we can take in a steel air kind of a scenario with the half of dBT and the half of the MRT, and this band which about 10 degree to almost about 34 degree centigrade, and this band can be taken as the 90% accepted case or the 80% accepted case or something like that. So, the Berkeley University has provided the one of the thermal comfort scale. We will see that one, or you can actually visit their website with this is with this, and you can check the differential kind of the parametric variations, and then you can find out the what is the comfort scenarios or so. The last one is the predicted thermal comfort, where PMV and PPV has been defined. PMV, the predicted mean mode, this particular Franger is one of the scientists in this area and the stalwart in this in his research, very fundamental and the very early research. He has devised a PMV, Franger the thermal equations, the predicted mean vote. He has selected lot of people, did lot of the experiment on them, and create a kind of equation which gives a PMV as a exponential kind of equation of this particular values, where m stands for the metabolic rate and 2 constant and the exponential multiplied by the thermal load. And against that he also found out the how people behave or how people find that particular scenario with a certain amount of PMV predicted mean vote, that how much percentage is dissatisfied. So, that PPD, that is called PPD, is also a function, or it is a linked with the PMV, and it is exponential way to link with 100 minus 95 exponential of this PMV. So, it is a exponential graph, and then he has devised this to. So, what we have to do, we have to first find out the PMV. So, PMV, as we discussed, this is the big equation, the thermal load. In fact, this L, this thermal load is nothing but this L. This is your this L, this L is your this one, this is your L is a big one, and this big equations actually taken care of your metabolic rate m, W the rate of mechanical work FCL is the ratio of body surface area, while clothing is on to a or clothing is off. These two scenarios, or maybe whatever, how much is the surface body surface area. TCL, clothes temperature, what is the temperature of the cloth. TMR is the mean radiant temperature. TAI is the DVT of the air. HC is a convective heat transfer coefficient of the air, and C1 and C2 are the two coefficients which depend upon the metabolic rate, work, and the DVT and vapor pressure. So, it is a complex scenario of complex equations also. Based on that, PMV can be calculated, and that is the number, and this number can be given with this particular equation to get the PPD. So, suppose this PMV, this number actually will lie either -3 to +3, this is range between this will fly, or it will fly between these two numbers, -3 to +3. Now, the equation is such a way, it is exponential equation is such a way the generated that this PMV will lie -3 to +3, and what is mean by +3 or near +3, that is very hot. So, the combinations of metabolic rate, the flow values, and all these things are such a way that gives you almost like 2.7, 2.8, 2.9, which is very hot scenario. +2 means it is warm scenario, +1 is slightly warm scenario, 0 is neutral. Similarly, if it is -1, it is a slightly cool, -2 is cool, and -3 is cold. So, based on that, it is a deeping kind of a curve, and suppose you are neutral, that means 0, your the PMV value based on your metabolic rate, your clothing, the DBT, MRT, everything is almost 0. So, you are here. So, that means at least what is the PPD? PPD is almost about 5% or so. That means the 5% is the percentage dissatisfaction. So, only out of the 100 people 5% may still believe that this neutral thing is not so good, I mean not so neutral kind of a thing, or it is not, they are not satisfied. Similarly, if you take a very high value, maybe it is 2.9 or something A here, which is very hot, very hot. So, then if you see what is the PPD value is almost 95%. So, that means 95% will be dissatisfied, where 5% may be still satisfied that yes, this is not so much, not so. So, it is not going to be always 100%. So, it is going to be neutral also, there is 5% is dissatisfied, and in case of the almost close to 3 is also maybe 5% is satisfied. So, something like that it will move also. So, it is a very interesting curve, and this curve is in the years and after years doing I mean after the lot of research and down the timeline, it has been rectified or modified with the different type of scenarios or so, but this is the one of the baseline we can think. And before we go to the next one website, and then we will see this Berkeley, the Center for the Built Environment, the thermal comfort tool. So, that website address I have given. So, this is the at present scenario. You see, these are all the parameters. We have a operative temperature 25 degree centigrade. We have the next one is the air speed, relative humidity 50%, metabolic rate, and flow value. So, 1, 2, 3, 4, 5, of course, this operative temperature has taken care of the DBT and MRT. So, there are 6 factors, and this is this point at present. So, suppose if I increase the med value, that means I am, or maybe if I increase the flow value instead of 0.61, suppose we go for very high flow value. So, I am still here, but the comfort zone is somewhere here, this blue one. So, this is I may feel warm, I may feel very warm. Okay. So, let us go back to the its 0.6 or something. So, 0.6 or something over here. Now, if I increase the metabolic rate, so I may still neutral. If I go little bit more, I may be slightly warm. If I go little bit more, I may be slightly warm or very warm or something like that it will go. So, let us go back to the perfectly 1 scenario 1, and now suppose the operative temperature is going to be suppose high. If it is high, then it is then I have to reduce the MET, then it is fine, then it is neutral. So, I have to sleep or I have to go lay down, or if I want to go for 1, then I have to reduce the clo value, then I have to remove the clothes, then I may be little bit neutral also. So, like that you can have those kind of the changes, and you can see the other changes of the scenario. This is a very interactive kind of a curve to understand the thermal comfort and how the med value, clo value and the humidity. Suppose I have increased further 30 degree and also it is warm and humid climate is almost 84 degrees. So, it is very slightly warm scenario, and if I increase that time med value. So, I am doing some kind of a lot of exercise or so, then you are going further beyond or so. Then in that scenario, if you increase the clo value and it will be warm or something like that. So, we are doing just reverse. So, what we have to do? You have to reduce this value. No, 0 may not be the good value. So, but your mate activity has to be very. So, then probably you are slightly warm kind of a scenario. Here what we can do? We can increase the air speed. So, if you increase the air speed, you can be neutral. So, it is humid. So, you have to increase the air speed. So, it will be neutral. If you increase the air speed too much, so you feel slightly cooler, and again if you decrease the temperature too much, you will be cold. It will be very cold. 16 degree temperature with 1.7 air speed will be really very cold. So, that way we can think this can be a very interactive kind of a curve. So, let us go back to the PPT, and then this is also Indian model. So, in the SP41 they have given the dry bulb temperature, relative humidity and the wind speed. What will be the wind speed scenario? Based on that, those are the comfort scenario, and those plus signs are the acceptance for the not those acceptable in the practice. Higher than that, and point the star dots points are it is not possible. So, there is another kind of a scenario which is given in our SP41, which is called the tropical summer index, which is also applicable in our country. So, the formula is this is the TW is the wet bulb temperature, TG is the globe thermometer temperature, V is the air speed. So, we have in this particular the tropical summer index, they have taken the RH, they have taken the globe temperature, which is close to the dBT and also the speed of air. So, those temperature has been taken into account, and this particular TSI can be computed. So, if you know the globe temperature and all those kind of the dBT wet bulb temperature and the velocity, you can calculate that one and go to the next slide, or in that particular SP41 there is a graph, and this hatched portion in the graph gives you the comfort zone, and it has a boundary. The boundary, what it is written over here, TSI value between 25 TSI value between 25 to 30 degree with the optimum condition is 27.5 degree. That is the optimum condition for the TSI, that is the tropical summer index. If it is above 30, that means 30 to 34, it is hot, warmth. If it is more than 34, that means more than 34, more than this 34. So, this is the 34, it is very hot or above the limit, whereas it is 25 to 30. So, if it is 19 to 25, it is okay, it is lower side cold, but if it is below 19 degree, it is too cold. So, if it is below 19, then it is too cold. So, these are the another way, another Indian way in the sense this is generated by the SP generated by scientist, Indian scientist, and given in the SP34 for our tropical climatic condition. So, that also can be taken into account. We will see that how that can be implemented in the further lectures in the when we go for the energy audit or maybe the energy retrofit. So, what we have discussed is that here is the thermal comfort parameters, PMB, PPB and some other indices. Thank you very much.